Hello everyone, I am Sci Geek, and we are getting ready to go on to some integral calculus of vectors. So this is some Calc 3 work, all on the preparation to learn the properties needed for electromagnetism. So we are going to start out by talking about line integral. So now a line integral is simply the integration of a vector field along a given line. So you could have some type of vector field, and you want to know how that vector field will affect a point along the line. So, how do we do that? Well, we start out by expressing the line integral as this vector field dotted into an infinitesimal line element. Now remember, the line element is defined back in equation 22, which is this. So dx, dy, dz, z hat. And it has to be described from a point so if we have our line from some point A. Hey, Lucian, how are you doing? Welcome in. Thank you for the follow. How are you doing today? We are just talking about some integral calculus. So, we are defining some dl. It's a vector. And we have some point along a line going from A to B. Now, when we look at this point, if the path is a closed loop, we simply denote that A equals B, which is very straightforward, and we define the loop as an integral sign with a little circle. This is the electrodynamics book. This is Griffiths' Introduction to Electrodynamics. And we are in chapter 1.3, looking at integral calculus. If you want, you can go Google the name of the book, and there are lots of resources that go through where you can get it. But what are you interested in? Are you interested in college level math, or are you interested in physics, or you have this book already? Oh yeah, it's a very good book. I have the third edition of this book when I took the course. And I have his quantum mechanics book, which might be future lessons from now. I might do some quantum. Yours is in Portuguese. Well, I'm glad he's translated to multiple languages, because David Griffiths has a knack for condensing down very complicated subjects into very simple language. back to line integrals. So if you've already taken Physics 1, you've already done work with line integrals. So you've done definition of work, which is done by the integration of the force along a line dl. So, if we want to calculate the integral along the path, there are two ways to go about this. One is path dependent and one is path independent. One where you will get a different answer depending on if you go from A to B in this curved line or in this line or in this line over here. Each one will give you a different answer. And you want to find the one for your particular curve, for your particular path. If you have a field that is conservative, then this doesn't matter. You just need to know the value of the integral at A, the value of the integral at B. The path is completely independent. So let's look at an example. We have a line integral from, in this vector field, so we have V is defined as y squared x hat plus 2x times y plus 1 y hat. From point A equals 1, 1, 0 to point B equals 2, 2. Gamer Strongman, how you doing? You hate science? Well, good thing we're doing math. How's everything going, Gamer Strongman? How was your workout this morning? None of these nuts jokes. It was good? Oh, I'm glad to hear. So first, I need to get a tablet eventually because this drawing with the mouse thing is for the birds. Some big brain shit. This is calculus. So all we are doing we are doing a line integral along the path from A to B of the vector dot dl. You did calculus once, you called it ULUS? The ULUS. Calculus. The ULUS. Aha. I get it. I get what you're saying. So this is typically done in the third semester of calculus. After you've done integration, you do line, surface, and volume integration, as well as some coordinate transformation stuff. So, first, we want, so we're going from let's see, figure 2, 1. All right. So this is X. This is Y. We're going from A to B. Do, 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 do. We need the antiderivative of the derivative of the integral of the function. You don't know what you're talking about. All right. Well, that's why I'm here, to go over the definitions. So part 1, we, along the paths 1 and 2, what is the loop that goes from A to B along 1 and then returns along 2? So this is part 1, and this is part 2. 1, 2. There we go. So, A, B. So, first thing we need to do is we need to find the integration along this first part here. So, that is in the x direction. So for part 1, so this whole integral is equal to the integral of A to point 2, 1, 0 dot dx x hat plus the integral of 0.210 to point B of v dot dy y hat. Okay, so let's break this up. So part 1. This is how we beat Wolverine? Yes, this is how we become Magneto. Your cat is bitching. Take care of your cat. So, first part. We have v dotted into x and only x. So this term becomes 0. So we have integral from A to point, let's call this point P, or let's call it point C. A to C, and that is going to be equal to y squared dx plus the integral from point C to point B of this. So that'll be 2xy plus 1, 2x y plus 1 dy. Okay, and then we just evaluate these two integrals. So you redeemed a flex? I should change these. And y is 1. So y is 1. So we have 1 squared dx. Y doesn't change at all. So we have the integral of a to c of 1 squared dx. And then we have the next one, which is the integral of c to b of x is equal to 2. So we have 4 times y plus 1 dy. So this becomes x evaluated from 1 to 2. This becomes b 4y plus 1. That's going to be equal to 4y becomes 8y squared? No, 2y squared. Y over 2. So they pull out a 4. So we've got 4 times quantity of y. Integral of y dy is going to be y squared over 2 plus y evaluated from 1 to 2. And we evaluate this out. This is going to be 2 minus 1. 2 minus 1 plus 4 times 4 over 2 plus 2 minus 4 times 1 over 2 plus 1. So this is equal to 1. This is equal to, let's see, 2 plus 2, 4 is 16 minus, this is a half plus 1 is 3 halves times 4. Let's see, that's going to be 4 over 2, which is 2 plus 4. 2 plus 4 is 6. 6 equals 11. Okay. All right. So that's part 1. Let's see if we can erase. So we have let's see if I can scroll. There we go. So, now let's do 2. So, we've got x equals y along path 2, and that should be a y. Here we go. So dx equals dy, dz is 0. So dl equals dx x hat plus dx x y hat, keeping everything in terms of x. And v is equal to x squared x hat plus 2x x plus 1 y hat. So now we dot and we go and we roll from A to B. And we have dl dot, the x hat component is going to be x squared dx plus, that's going to be 2x squared, 2x squared plus 2x dx plus. That's going to be equal combining terms, A to B. We have 3x squared plus 2x dx. So that is simply integral from 1 to 2, actually evaluated from 1 to 2. So that's simply x cubed plus x squared from 1. What did you study for a PhD? I studied physics. I studied mostly radar scattering, so electromagnetic scattering. So EMag is my baby. I know a lot about EMag. So we evaluate this from 1 to 2, and we have, let's see, we've got 8 minus 1 plus 4 minus 1. So that's 7 plus 3 is 10. Okay. So now we want to go part 3. We want to find the loop of V dot dl. Well, we know that part 1, going to apply for a master's degree in, here? Nice. Do you have an area of focus? Are you going to be looking at some mechanical stuff, electrical stuff? What are you interested in? So if we have our loop, we have part 1, which is equal to integral of part 1. You like quantum mechanics? Ah, quantum mechanics is very fun. Typo here. Minus, because we're going the opposite way. Here we go. Easy, no? So, should have put that on the big whiteboard. That would have been a lot easier than looking at my tiny scratch. So that is the line integral. You break down the function into different values. You define the path that it's taking. So you need to define how dl is changing, going forward and back. So then we have the surface integral. So we have, let's see if I can, so we have some vector times some dA, where dA is some infinitesimal element with a normal direction pointing outward from the material. So, outward is positive, inward is negative. We can then define what is called the flux, which is how much stuff is passing through some volume or through some surface. So, like the line integral, the surface integral is going to be dependent on the integration of the surface. So let's look at this next example. They want to calculate the surface integral of this vector field, which has an x, a y, and a z component in the 5 sides of the cube. So we want to calculate the surface integral over 5 sides. So we look at side 1, x is equal to 2. So dA is just dx dy x hat. Sorry, dy dz. So we plug in our value for x and then propagate out. For part 2, our x is 0. So 1, 2, 3, 4, and then 5 is up. So again, x doesn't change, so we keep that constant. We plug in the value of x, define what dA is, and then solve. For 3 and 4, y is constant. So y is equal either 2 or 0, depending on which face we're looking at. And our area is dx dz in the y hat direction, or the negative y hat direction, depending on which side we're looking at. And finally, our fifth face is equal to 2. Z is equal to 2. The area is only on the dx dy. But we solve it out and we get our last value. Adding all of those together, we get 20. Volume integrals. So, volume integrals are a bit simpler because we don't need to deal with the vectors, which makes things more convenient. So if we have this volume integral, t dt. So if t is the volume function, the density function, and then dt is our infinitesimal volume. So if we multiply the density by the volume, we get the mass of the object. So if the mass is changing, some non-homogeneous fluid or something like that, then this is solved like any other volume integral. You have your function that's defined by t, and you just integrate in log x, y, and z. It's a triple integral. It's very straightforward. If we have to do a vector function, the volume integral of a vector function, the unit vectors are constants. So those pop out of the integral, and then we just solve the component, where dt is dx dy dz. And then we got another function. So this is really easy. So we've got our density function, and we just integrate one at a time. We integrate x with y and z constant, then we integrate y after solving for x, then we integrate z after solving for y, plug all those values in, and we get 3/8. Okay. So now we get to the fundamental theorem for calculus. Which we have the derivative of a function. The integral of a derivative of a function is equal to the function evaluated at b minus the function evaluated at a. How to integrate f of x. You think of a function f whose derivative is equal to capital F. Suppose we have a scalar function. Starting at a point A, we move a small distance. According to the equation, the function t will change by some amount. We had a small displacement. Incremental change will be in the gradient of that displacement. At each step, we compute the gradient of t at that point and dot it into this displacement and give us the change in t. Eventually, the total change in t is going from A to B along the path selected is the gradient of t dotted into dl is equal to the function of t at B minus the function of t evaluated at A. The line integral of a derivative, the line integral of a gradient, is given by the function at the boundaries, a and b. So, the fundamental theorem for divergences, moving on, states that the divergence of a volume is equal to the surface function. So the facets within the volume is equal to the flow out through the surface. This is known as Gauss's theorem, Green's theorem, divergence theorem. It is very important to remember. So we want to, it is boxed. This is a very important equation because it allows us to turn a volume integral into a surface integral back and forth. So, fundamental theorem for curls is Stokes' theorem. And again, this allows a surface integral to go into a line integral. So the curl of a vector along the surface is equal to the line integral of the line bounding that surface. So we got problems, integration by parts, and then we get into the next section, which is curvilinear coordinates. So, this is all Calc 3 work. So, let's get into curvilinear coordinates. So curvilinear coordinates, you can label a point in the Cartesian plane by x, y, and z. You can also label it in terms of polar or spherical coordinates. In fact, there are a multitude of different coordinate systems that you can, not an infinite amount, but just a handful, where you can define different functions. So let's look at spherical coordinates first, because those are the most intuitive. You have some point along a sphere, and we have y, z, x. We have some point on the sphere. So this R I did that backwards. So we have our theta here and our phi So the r unit vector is simply the spherical coordinates of the vector a, b, and of r, theta, and phi. Converting those into as rectangular coordinates, we have 164 here, where we have the unit vectors r, theta, and phi. This is going to be something for easy reference, but is very useful. And finally, we have our infinitesimal displacements. So we can have a change in r, we have a change in theta, or we can have a change in phi. So if we are only changing in one direction, then dr is just dr. There's no change. There's nothing else to it. But the dl along the theta direction is r d theta. The dl along the phi direction is r sine theta d phi. So the final unit vector L is given here. So very useful for line integrals and the like. Finally, we have the volume integral, which is just the components of the dl d theta d phi, which is going to be r sine theta times r d theta times dr, r squared sine theta dr d theta d phi. If we have a surface, then we just simply multiply the elements of that surface, and we get our area that's constant in r. Here's one where it's constant in theta. So easy to think of, easy to work with. So now let's start. I'm going through these quick because these should be done in your Calc 3 course in more detail, and it should also be used as a reference in the back of the book. So here we have the chain rule to expand out the partials. So changing the gradient of t with respect to x, r, theta, and phi. So here we have the gradient, the divergence, and the curl, and the Laplacian of spherical coordinates. You should never have to remember these. You should always just know how to apply them. Know that I'm in a spherical coordinate system, so I'm going to use my divergence or my curl in that coordinate system. Look it up. Very straightforward. Now we can do the same thing for cylindrical coordinates, which is simpler. We have z is the same as Cartesian, but we have a theta and an s, or a rho. So infinitesimal displacements, unit vectors, gradient, divergence, curl, Laplacian. Here we go, and the volume element. Dirac delta function. The Dirac delta function, we will skip over that, but needless to say, when you integrate over a Dirac delta function, it sifts out the value at that function. So this is the main property that you want to look at. F times the Dirac delta function of x dx is the Dirac delta function, the function evaluated at 0, times the integral of the Dirac delta function. The area of that is just 1, so you just have the function. Generalized to an arbitrary point, Dirac delta function here. X minus a is equal to f of Dirac delta x minus a is equal to x a. So simple integral here. We have our evaluated from 0 to 3. So we plug in 2. It's evaluated. Its area is 1 underneath the curve. So this is equal to 2 cubed times Dirac delta x minus 2. Very simple. That becomes 8. That's a weird way to erase. Okay, so we've got the Dirac delta function. The three-dimensional Dirac delta function, very similar. Theory of vector fields and potentials. We will go over in more detail later. So then we have a bunch of problems that we can go over. So that is chapter 1 of electrodynamics. So I am going to call it right there. And next time we stream, we're going to go into electrostatics. So actually getting into EMag. So thank you all very much for streaming and watching me. Thank you all for joining and following me. Take a look if you're interested. We will go on further adventures into electrostatics. So, this is Sci-Guy Geek, and I am signing off. So, take care, everyone. I'll catch you all later.